I'm Jim Cooper with Sonrisa Research, a nonprofit company in Santa Fe, New Mexico, and I'm partnering with XFAB Texas to develop silicon carbide CMOS smart power ICs, and to do this with increased short circuit withstand time. Now, there are actually two aspects to this project. First, the smart power ICs. This is a really new thing for silicon carbide, and we'll talk about that in a few minutes. The other aspect is to increase the short circuit withstand time using a process we call gate charge scaling. Because of the time constraints, I won't be able to talk about both of these this morning, so I'm going to focus on the smart power ICs. Here's a cartoon of a power DMOSFET, the type of device that's in production at XFAB today. We're going to take this process and implement CMOS circuits on the same wafer. What I'm showing on the left is a simple CMOS inverter. We have an N-channel MOSFET. We have a P-channel MOSFET. We can superimpose the circuit diagram here, and you can see that these would be connected as shown to implement a logic inverter. Now, we can get this type of circuit with very few additional processing steps. We use the aluminum implant for the P base of the DMOSFET, and we use that to form the body of the N-channel MOSFET in the CMOS circuits. We take the N+ implant and we use it here for the source drain of the N-channel MOSFET. The P+ base contact implant forms the source and drain of our P-channel MOSFET. All of these things come along for free. The only thing we have to do is add an isolation here layer to separate the N well from the underlying drift layer, because the drift region and the substrate are going to be at a high positive voltage. It turns out we can do this with just one additional implant. It's a complex implant because we form the deep P isolation layer, and above it we tailor in the doping for the N well that resides under the P-channel MOSFET. As I said, it's a very simple process. We can do it with only one additional implant and one mask above that of the standard DMOSFET process. CMOS digital logic is very robust with respect to variations in threshold voltage, power supply, and temperature. And we can also implement complex analog circuits such as comparators and op-amps, and we can use them for sensors and protection circuits. And I'll talk more about that in a few slides. We're developing a library of polycells that contain the basic logic gates. What I'm showing here, these are the P-channel MOSFETs in the top row. They're connected to N-channel MOSFETs in the row below. Running along the bottom, this metal line is our ground line for all of the cells, or our VSS line. And along the top is our power supply line for the cells. At each end, we have polycells that establish the body bias for the N-channel and the P-channel MOSFETs. Here's a logic inverter, a 2-input NAND gate, a 2-input NOR gate, 3-input NAND, and a 3-input NOR. And we can take these 5 basic gates and implement much more complex digital circuits. So here's a row of those basic gates. I'm going to flip them over and put another row up here so that they share the same VDD power supply line. On the lower left here, we're implementing an exclusive OR gate. The lower right is a half adder, and the circuit on the top is a full adder. So I mentioned that CMOS is very robust. Here I'm plotting the transfer function of a CMOS inverter. On the vertical axis, I'm plotting the output voltage of the inverter normalized to the supply voltage. On the horizontal axis is the input voltage normalized to the supply. And you'll see the blue curve, or at least 3 blue curves. This is the transfer function, and it shows the output voltage as a function of the input voltage. And you can see we're plotting for 3 different power supplies, 20 volts, 10 volts, and 6 volts. You can see the curves are very, very similar, very tolerant of the power supply variation. Now, to see the operating point, we take those blue curves and we plot them on opposite axes. So we plot the input axis on the output and the output on the input, we get the red curves. So the intersections here are the stable operating points. The logic 0 operating point is at ground on the left, upper left. The logic 1 operating point is at VDD on the right. So the logic swing goes all the way from ground to VDD. The intersection point here is the switching transition. You can see it lies right at half the supply voltage, and this is true regardless of how the supply voltage varies. The voltage swing between the stable operating point and the transition point is our noise margin. And again, it's very stable with respect to variations in supply voltage. It's also very robust with respect to variations in temperature and threshold voltage. Now, we've been doing fabrication at XFAB. We began processing in October of 2019. We took 12 wafers through. We held 6 just before implant anneal, and we completed 6. And these first 6 came out in late February. This is split number 1. We did automated wafer probing for several weeks. And then in April, we went over and did on-site manual probing. On the left is the 150 millimeter wafer. The shiny rows are the power D MOSFETs. The darker rows in between are the integrated circuits and the process control monitors. The N-channel MOSFETs and the CMOS circuits look very good. Here's the drain current versus drain voltage for gate voltages running up to 20 volts. We can plot the drain current versus gate voltage and extrapolate that to 0 drain current. We find a threshold voltage of about 7.5 volts. We'd like to get this down to around 3.5 or 4 volts. We will do that on the next run with the threshold adjust implant. The P-channel MOSFETs are rather poor. You can see they don't turn on until about 22 volts negative on the gate. The currents are low, and here at the origin, you can see the weird shape is due to poor P+ source drain contacts. Now what I'm plotting here is not the drain current, but it's actually the source current. Normally the source current and drain current are the same, but in this case the drain current has an added component, and it's due to a drain leakage that occurs when the drain is at 20 volts bias. That leakage current is associated with the problem we're having with our P+ contacts. And so after having determined that we had poor P+ contacts on the first 6 wafers, we took 2 more wafers through the remainder of the process using a modified P+ contact process. We took 2 more wafers through with a modified process and a P-channel threshold adjust to reduce the threshold voltage. Split number 2 came out several weeks ago. It's currently being characterized. Split number 3 is almost completed through the process. Now where we'd like to go next is to do a full protection circuit. So imagine that this dashed rectangle is your power MOSFET die. The actual MOSFET is shown at the far right as a very small symbol because I want to leave room for the protection circuits. So we're going to put on an over temperature sensor and an overcurrent sensor. Each of these requires 1 op amp, you can see on the left side, and this can be implemented with about 24 transistors. We combine them with a signal combiner, and we use that to drive a transmission gate and a clamping MOSFET. So the way this would work is if you detect an over temperature or an overcurrent situation, either one, we will break the transmission gate, disconnect the external gate drive, and clamp the MOSFET gate to ground, turning it off rapidly. Let me summarize. CMOS technology can enable on-chip sensing and clamping circuits to create a self-protecting power MOSFET, and that's very exciting because now you could tell your customers you don't have to worry about protecting this device. It'll turn itself off if needed. Our initial goal is to optimize this process. We want to verify this digital polycell library that we're creating. We're going to get SPICE data for SPICE models, and we're going to create a design kit, a PDK. And in future work, if funded, we're going to implement analog and mixed signal circuits. And these will be these on-chip temperature and current sensors and these protection circuits that I just discussed. Now that's all the time I have. If you have questions or have comments, I invite you to contact me by email. My email address is cooperj@purdue.edu. Thank you for your attention.